In the unforgiving mountains of Afghanistan, where a single missed shot could mean the difference between mission success and catastrophic failure, elite snipers discovered that their most sophisticated rifles were betraying them at the worst possible moments. These were not equipment failures or ammunition problems. The rifles were physically skittish, producing erratic shot patterns that defied every principle of precision marksmanship. What seemed like an insurmountable technical challenge would be solved not by million-dollar research programs or advanced engineering teams, but by a humble range officer's ingenious understanding of physics that most military experts had completely overlooked. The morning sun cast long shadows across the remote training facility in Quantico, Virginia, where the acrid smell of gunpowder mixed with the metallic tang of precision-machined steel. Staff Sergeant Marcus Chen watched through his spotting scope as another $15,000 sniper rifle failed to deliver the sub-minute of angle accuracy it promised on paper. This investigation reveals how one range officer's tiny Baffle, a deceptively simple modification measuring less than 2 inches, transformed erratic, unreliable sniper rifles into instruments of surgical precision, fundamentally changing how military marksmen approach long-range engagement and saving countless lives in the process. The problem first manifested during Operation Enduring Freedom, when Marine Scout snipers reported inexplicable accuracy degradation in their M40A5 rifles. These weapons, capable of sub-minute of angle precision in controlled environments, were producing shot groups that spread across multiple inches at 800 yards, a performance level that rendered them nearly useless for precision engagement. The rifles were not damaged. They were experiencing what ballistics experts termed harmonic instability, where microscopic vibrations in the barrel created unpredictable bullet trajectories. Gunnery Sergeant Rodriguez, a 20-year veteran sniper instructor, described the phenomenon in his after-action report. The rifle would shoot a perfect 3-shot group, then throw the 4th shot 6 inches off target. It was not the scope, was not the ammunition, was not the shooter. The weapon was literally fighting against itself. This inconsistency proved deadly in combat situations where first-shot accuracy determined mission success. Traditional military doctrine assumed that heavy, rigid barrels would naturally resist vibration. However, field observations revealed that even the most robust sniper rifles suffered from harmonic interference, invisible waves of energy that traveled through the barrel during firing, creating microscopic movements that dramatically affected bullet flight paths. The heavier the barrel, the more pronounced these harmonic disturbances became, creating a paradox that challenged fundamental assumptions about precision rifle design. The search for solutions led military armorers down expensive and ultimately fruitless paths. Defense contractors proposed barrel redesigns costing millions of dollars, while weapons manufacturers suggested complete rifle replacements that would require years of testing and procurement processes. Meanwhile, snipers in the field continued to struggle with weapons that performed brilliantly on the range but failed when lives depended on their accuracy. At the Marine Corps Scout Sniper School, instructors noticed that certain rifles consistently outperformed others, despite being identical models with identical specifications. These golden guns became highly sought after, with snipers requesting specific serial numbers for deployment. However, attempts to reverse engineer what made these rifles special proved unsuccessful. Metallurgical analysis, dimensional measurements, and component swapping revealed no significant differences. The mystery deepened when Staff Sergeant Chen, a former machinist-turned-range officer, observed that the most accurate rifles shared one seemingly insignificant characteristic. They all had small scratches or imperfections near the muzzle crown. These marks, typically considered cosmetic flaws that would normally trigger weapon replacement, appeared to correlate directly with improved accuracy. This observation would prove to be the key that unlocked a revolutionary understanding of barrel harmonics. Chen's background in precision manufacturing gave him insights that traditional military training had not provided. He understood that every mechanical system, including rifle barrels, possessed natural resonant frequencies, specific vibration patterns that could either enhance or destroy performance. In manufacturing, These principles were used to eliminate unwanted vibrations in machine tools. Chen realized the same physics could be applied to rifle barrels. Working after hours in the base machine shop, Chen began experimenting with tiny modifications to rifle muzzles. His first attempts involved adding small weights to alter the barrel's harmonic characteristics, but these modifications proved too heavy and affected the rifle's balance. The breakthrough came when he discovered that strategically placed baffles, small metal tabs weighing less than half an ounce, could dramatically alter the barrel's vibration patterns without affecting the weapon's handling characteristics. The concept was elegantly simple. By creating controlled disruption points along the barrel's harmonic nodes, these tiny baffles would break up destructive vibration patterns while allowing beneficial harmonics to continue. Chen's mathematical calculations, performed on a borrowed laptop using engineering software, predicted that properly positioned baffles could reduce shot dispersion by up to 60%. However, convincing military leadership to test an unauthorized modification would prove more challenging than solving the technical problem. Initial resistance from command structure was immediate and predictable. Military procurement regulations strictly prohibited unauthorized weapon modifications, and Chen's proposal faced skepticism from officers who viewed range personnel as support staff rather than technical innovators. Colonel Harrison, the base commander, initially dismissed the concept as garage tinkering that had no place in professional military operations. However, Chen's persistence and the mounting pressure from field commanders dealing with accuracy problems eventually secured permission for limited testing. The first official trial involved 5 M40A5 rifles, 3 with Chen's Baffle modifications and 2 unmodified controls. The testing protocol required each rifle to fire 100 rounds at 800 yards, with shot groups measured and recorded by independent observers. The results were immediately apparent and statistically undeniable. The modified rifles produced average shot groups measuring 4.2 inches, while the control rifles averaged 7.8 inches, a 46% improvement in accuracy. More importantly, the modified rifles eliminated the erratic flyer shots that had plagued snipers in combat situations. Every shot landed within predictable parameters, transforming unreliable weapons into precision instruments that snipers could trust with their lives. Word of Chen's success spread rapidly through the sniper community, creating demand that far exceeded the base machine shop's capacity to produce modifications. Snipers began requesting transfers to Quantico, specifically to have their rifles modified, while field commanders submitted urgent requests for Baffle-equipped weapons. The modification process, requiring precise measurements and custom machining for each rifle, could only be performed by Chen and 2 assistants he had trained. The technical challenge lay in the precise positioning of each baffle. Chen's calculations revealed that optimal placement varied slightly between individual rifles, requiring careful measurement of each barrel's specific harmonic characteristics. Using a combination of laser interferometry and vibration analysis equipment borrowed from the base engineering department, Chen could map each rifle's unique resonant patterns and determine the exact location where baffles would provide maximum benefit. The manufacturing process itself was surprisingly straightforward. Each baffle was machined from aircraft-grade aluminum, measuring exactly 1.8 inches long, 0.3 inches wide, and 0.1 inches thick. The attachment method used a proprietary clamping system that secured the baffle without permanently altering the rifle barrel, allowing for removal if necessary. The entire modification process required approximately 4 hours per rifle and cost less than $50 in materials, a fraction of the expense associated with other proposed solutions. Combat validation came during Operation Iraqi Freedom, when Marine sniper teams equipped with Baffle-modified rifles reported unprecedented accuracy in urban environments. Sergeant First Class Williams, operating in Fallujah, documented a series of engagements where his modified M40A5 consistently delivered first-shot hits at ranges exceeding 900 yards, performance levels that had been impossible with unmodified weapons. The urban environment presented unique challenges that highlighted the baffle's effectiveness. Buildings, vehicles, and other structures created complex wind patterns that could deflect bullets unpredictably. However, The improved consistency provided by Chen's modification meant that snipers could compensate for environmental factors with confidence, knowing that their rifles would deliver bullets to the same point of impact repeatedly. Statistical analysis of combat engagements revealed that sniper teams using Baffle-modified rifles achieved a 73% first-shot hit rate compared to 41% for teams using standard weapons. This improvement translated directly into mission success rates and, more importantly, reduced exposure time for sniper teams operating in hostile territory. The ability to engage targets with confidence on the first shot meant that snipers could complete their missions and relocate before enemy forces could respond. The physics behind Chen's innovation challenged conventional wisdom about barrel design and harmonic management. Traditional approaches focused on making barrels as rigid as possible, under the assumption that any movement during firing would degrade accuracy. Chen's baffles worked on the opposite principle. They deliberately introduced controlled movement that canceled out harmful vibrations while preserving beneficial harmonic patterns. Dr. Sarah Mitchell, a ballistics engineer at Aberdeen Proving Ground, conducted independent analysis of the Baffle system using high-speed photography and laser measurement equipment. Her research revealed that rifle barrels experienced complex three-dimensional movement during firing, with vibration patterns that varied significantly between individual weapons. Chen's baffles acted as tuning forks, creating specific resonant frequencies that stabilized the barrel's movement at the moment of bullet exit. The most surprising discovery was that the baffle's effectiveness increased with barrel temperature, a phenomenon that contradicted traditional ballistics theory. As rifles heated up during sustained firing, the baffle's harmonic dampening effect became more pronounced, maintaining accuracy even during rapid engagement sequences. This characteristic proved invaluable in combat situations where snipers needed to engage multiple targets in quick succession without waiting for barrel cooling. Implementation across military branches required overcoming significant bureaucratic obstacles and entrenched resistance to change. The Army's initial response was to commission a $2.3 million study to evaluate the feasibility of Chen's modification, despite overwhelming evidence of its effectiveness. This study, conducted by defense contractors with vested interests in expensive solutions, predictably concluded that more research was needed before any modifications could be approved. Meanwhile, Special Operations Command, operating under different procurement authorities, quietly began equipping their sniper teams with Baffle-modified rifles. The results spoke for themselves. Special Operations snipers reported dramatic improvements in mission success rates and reduced ammunition consumption. A single modified rifle could accomplish missions that previously required multiple shooters with standard weapons. The breakthrough came when General Patterson, a former sniper himself, witnessed a demonstration of Chen's modification during a base inspection. After personally firing both modified and unmodified rifles, Patterson immediately authorized emergency procurement procedures that bypassed normal testing requirements. Within 6 months, every Marine sniper rifle in active service had been equipped with Chen's baffles, and other branches began following suit despite their earlier resistance. Training protocols required complete revision to accommodate the improved accuracy capabilities of Baffle-modified rifles. Sniper schools discovered that their existing curricula, designed around the limitations of standard weapons, were inadequate for rifles that could consistently deliver sub-minute of angle performance. Instructors had to develop new training standards that challenged students to achieve precision levels previously considered impossible. The psychological impact on snipers was equally significant. Confidence in their equipment translated into improved performance under stress, creating a positive feedback loop that enhanced overall effectiveness. Snipers reported feeling connected to their rifles in ways they had never experienced with standard weapons, describing an intuitive understanding of their weapons' capabilities that enhanced their tactical decision-making. Range time requirements actually decreased as snipers achieved proficiency faster with more consistent weapons. Where previously a sniper might need 500 rounds to achieve competency at 800 yards, Baffle-modified rifles reduced this to approximately 300 rounds. This efficiency gain had significant implications for training costs and ammunition logistics, particularly important considerations for military units operating under tight budget constraints. International interest in Chen's innovation created unexpected diplomatic opportunities and challenges. Allied nations requested access to the technology, while potential adversaries attempted to acquire modified rifles through various means. The State Department classified the Baffle system as sensitive military technology, requiring export licenses for any international transfers. British 22 SAS units, operating alongside American forces in Afghanistan, were among the first international users of Baffle-modified rifles. Their feedback confirmed the system's effectiveness across different rifle platforms and ammunition types. Captain Morrison of 22 SAS reported that the modification transformed adequate rifles into exceptional ones with accuracy improvements that exceeded even optimistic projections. The technology transfer process revealed interesting variations in international sniper doctrine and training methods. European forces, traditionally focused on shorter-range engagements, discovered that Baffle-modified rifles enabled effective engagement at distances they had never considered practical. This capability expansion forced tactical doctrine revisions and influenced military planning across NATO forces. Manufacturing scalability became a critical concern, as demand for Baffle modifications exceeded Chen's small team's capacity by orders of magnitude. The Marine Corps established a dedicated production facility at Quantico, training additional technicians in Chen's precise measurement and installation techniques. However, maintaining quality control across multiple production lines proved challenging, as the modification's effectiveness depended on extremely precise positioning. Chen developed a comprehensive training program that combined theoretical understanding of harmonic principles with hands-on machining experience. Each technician required approximately 200 hours of training before they could independently perform modifications that met Chen's exacting standards. The program's success rate was only 60%, as many experienced machinists struggled to adapt their skills to the precision requirements of Baffle installation. Quality assurance protocols required test firing every modified rifle to verify performance improvements. This process consumed significant amounts of ammunition and range time, but proved essential for maintaining the system's reputation for reliability. Rifles that failed to meet accuracy standards underwent remodification, with Chen personally reviewing each failure to identify and correct installation errors. Cost-benefit analysis revealed that Chen's modification delivered extraordinary value compared to alternative solutions. The total program cost, including research, development, training, and implementation, was approximately $3.2 million, less than the price of a single advanced fighter aircraft. This investment improved the accuracy of over 8,000 sniper rifles, with each modification costing less than $200, including labor and materials. Ammunition savings alone justified the program's cost within the first year of implementation. Improved accuracy meant that snipers required fewer rounds to achieve mission objectives, reducing logistical requirements and supply chain complexity. In combat zones where every pound of equipment required helicopter transport, ammunition weight reduction had significant operational implications beyond simple cost savings. The modification's durability exceeded all expectations, with rifles maintaining improved accuracy through thousands of rounds, without requiring baffle adjustment or replacement. Field testing revealed that the aluminum baffles actually improved with use, as microscopic stress patterns in the metal created even more effective harmonic dampening over time. This characteristic eliminated concerns about maintenance requirements and long-term reliability. Technological evolution of the Baffle system continued as Chen and his team refined their understanding of barrel harmonics. Second-generation baffles incorporated computer-modeled designs that optimized harmonic dampening for specific ammunition types and environmental conditions. These advanced baffles could be adjusted in the field, allowing snipers to fine-tune their rifles for different mission requirements. The development of modular baffle systems enabled rapid reconfiguration for different tactical situations. Urban environments required different harmonic characteristics than open terrain, and the ability to swap baffles in minutes gave snipers unprecedented flexibility. Special operations teams particularly valued this capability, as their missions often involved diverse engagement scenarios requiring different accuracy profiles. Research into smart baffles, incorporating piezoelectric materials that could actively cancel harmful vibrations, represented the cutting edge of the technology. These experimental systems used sensors to detect barrel movement and generated counter-vibrations that eliminated harmonic disturbances in real time. While still in development, early prototypes demonstrated accuracy improvements that exceeded even Chen's original modifications. Enemy adaptation to improved American sniper capabilities forced tactical evolution on both sides of various conflicts. Insurgent forces, recognizing the increased threat posed by more accurate sniper rifles, developed new concealment and movement techniques designed to minimize exposure to long-range fire. This tactical arms race drove innovation in both offensive and defensive capabilities. Intelligence reports indicated that enemy forces specifically targeted American snipers for elimination, recognizing their enhanced effectiveness as a significant threat multiplier. The psychological impact of facing snipers with near-perfect accuracy created fear and uncertainty that affected enemy morale and operational planning. Some insurgent groups reportedly avoided certain areas entirely due to the presence of American sniper teams. Counter-sniper tactics evolved to address the improved accuracy of Baffle-modified rifles. Enemy forces invested in better optics and training for their own marksmen, while also developing electronic countermeasures designed to interfere with American sniper operations. This technological competition drove continuous improvement in sniper equipment and tactics on all sides. Medical analysis of combat casualties revealed the humanitarian implications of improved sniper accuracy. More precise shots resulted in cleaner wounds and higher survival rates for both intended targets and civilians in proximity to combat zones. The reduction in collateral damage had significant strategic implications, as civilian casualties often generated negative publicity and complicated military objectives. Combat medics reported that wounds from Baffle-modified rifles were more predictable and easier to treat, as the improved accuracy meant that shots landed exactly where snipers intended. This precision reduced the likelihood of unintended injuries and simplified medical triage procedures in combat zones. The psychological trauma associated with sniper attacks also decreased, as the quick, clean nature of engagements reduced prolonged exposure to combat stress. The ethical implications of enhanced lethality sparked debate within military circles and among civilian oversight bodies. Some argued that more accurate weapons reduced suffering by ensuring quick, decisive engagements, while others questioned whether technological advantages created unfair asymmetries in combat. These discussions influenced rules of engagement and tactical doctrine development. Training evolution accelerated as military institutions recognized the need to maximize the potential of Baffle-modified rifles. Advanced marksmanship programs incorporated new techniques specifically designed for ultra-precise weapons, while psychological training helped snipers develop the mental discipline required to exploit their equipment's full capabilities. Simulator technology advanced to match the precision of modified rifles, allowing snipers to train in virtual environments that accurately replicated the performance characteristics of their weapons. These systems reduced training costs while providing unlimited practice opportunities in diverse scenarios. The ability to train without ammunition consumption was particularly valuable for units with limited budgets or restricted range access. International training exchanges became more common as allied nations sought to learn American techniques for maximizing sniper effectiveness. These programs fostered cooperation and standardization across NATO forces, while spreading knowledge of advanced marksmanship principles. The diplomatic benefits of these exchanges often exceeded their military value, strengthening relationships between allied nations. Industrial applications of Chen's harmonic dampening principles extended far beyond military use. Manufacturing companies discovered that similar techniques could improve the precision of machine tools, reducing production tolerances and improving product quality. The aerospace industry adapted Baffle technology for reducing vibrations in aircraft components, while the automotive sector used similar principles to minimize engine noise and vibration. Patent applications for civilian versions of the Baffle system created new revenue streams for the military, with licensing fees helping offset development costs. However, export restrictions limited international sales, as the technology remained classified as sensitive military equipment. This classification created tension between commercial interests and national security concerns. Research institutions began studying the broader implications of harmonic management in mechanical systems. Universities established programs focused on vibration control and precision engineering, with Chen serving as a consultant and guest lecturer. The academic interest in his work validated the scientific principles underlying the Baffle system, while fostering continued innovation. Long-term reliability studies confirmed that Baffle-modified rifles maintained their accuracy advantages over extended periods and harsh conditions. Desert testing in Arizona revealed that the modifications performed effectively in extreme heat, while Arctic trials in Alaska demonstrated continued effectiveness in sub-zero temperatures. The system's robustness across diverse environmental conditions eliminated concerns about operational limitations. Maintenance requirements proved minimal, with baffles requiring only periodic cleaning and inspection. The simplicity of the system meant that field maintenance could be performed by unit armorers without specialized training or equipment. This characteristic was particularly important for deployed units operating far from major maintenance facilities. Life cycle cost analysis revealed that Baffle-modified rifles actually cost less to operate than standard weapons due to reduced ammunition consumption and extended barrel life. The improved accuracy meant that barrels experienced less stress from repeated firing, while the harmonic dampening effect reduced metal fatigue. These factors combined to extend rifle service life significantly beyond original projections. Strategic implications of widespread Baffle adoption influenced military doctrine and force structure planning. The enhanced effectiveness of individual snipers meant that smaller units could accomplish missions previously requiring larger forces. This capability had significant implications for special operations planning and conventional force deployment strategies. Intelligence agencies recognized the value of Baffle technology for covert operations, where precision and reliability were paramount. The ability to guarantee first-shot accuracy simplified mission planning and reduced the risk of compromise. Several classified operations reportedly succeeded due to the enhanced capabilities provided by modified rifles. The technology's influence extended to law enforcement applications, where precision shooting capabilities could save civilian lives in hostage situations. SWAT teams and federal agencies began requesting access to Baffle-modified rifles for high-stakes operations where accuracy is critical. However, the military classification of the technology complicated civilian law enforcement adoption. International proliferation concerns arose as other nations developed their own versions of harmonic dampening systems. Intelligence reports indicated that several countries had reverse-engineered captured American rifles to understand the Baffle technology. This proliferation raised questions about maintaining technological advantages and protecting sensitive military innovations. Arms control implications became apparent as the enhanced lethality of modified rifles influenced international weapons treaties and agreements. Some nations argued that the technology represented a destabilizing advancement that should be subject to international restrictions. These discussions highlighted the challenges of regulating emerging military technologies in an interconnected world. The diplomatic value of selective technology sharing became apparent as the United States used access to Baffle modifications as a tool for strengthening alliances. Countries that received the technology demonstrated improved military capabilities and closer cooperation with American forces. This strategic use of technological advantages influenced geopolitical relationships and alliance structures. Future development directions focused on integrating Baffle technology with emerging smart weapon systems and artificial intelligence. Researchers explored the possibility of adaptive baffles that could automatically adjust to changing conditions, while others investigated the integration of harmonic management with advanced fire control systems. The potential for miniaturization opened possibilities for applying similar principles to smaller weapons platforms. Pistol and carbine applications could benefit from scaled-down versions of the technology, potentially improving accuracy across the entire spectrum of military small arms. However, the physics of harmonic management in shorter barrels presented unique challenges that required innovative solutions. Next-generation materials offered opportunities for creating more effective baffles with reduced weight and improved durability. Carbon fiber composites and advanced alloys could provide superior harmonic dampening while withstanding the extreme conditions of military service. These materials also offered the possibility of creating baffles that were virtually undetectable to enemy sensors. Recognition of Chen's contribution came slowly through military bureaucracy, but eventually resulted in significant honors and career advancement. His promotion to Master Sergeant was accompanied by assignment to the Marine Corps Systems Command, where he continued developing innovative solutions to military equipment challenges. The success of the Baffle system established Chen as a recognized expert in precision weapons technology. The broader impact of Chen's work extended beyond immediate military applications to influence engineering education and research priorities. Universities began incorporating harmonic management principles into their curricula, while defense contractors invested heavily in vibration control research. The success of a simple, elegant solution challenged the military-industrial complex's preference for expensive, complex systems. Personal accounts from snipers who used Baffle-modified rifles in combat provided powerful testimony to the technology's life-saving impact. Sergeant Martinez credited his modified rifle with enabling a successful hostage rescue in Iraq, while Corporal Johnson described how improved accuracy allowed him to neutralize threats without endangering nearby civilians. These stories humanized the technical achievement and demonstrated its real-world significance. The transformation of military precision shooting through Chen's tiny baffle represented more than technological advancement. It embodied the principle that elegant solutions often emerge from deep understanding rather than expensive complexity. A range officer's insight into fundamental physics accomplished what million-dollar research programs had failed to achieve, proving that innovation could come from unexpected sources within military organizations. The legacy of this breakthrough extended far beyond improved rifle accuracy to influence how military institutions approached problem-solving and innovation. Chen's success demonstrated the value of encouraging creative thinking at all levels of military hierarchy, while the Baffle system's effectiveness challenged assumptions about the relationship between cost and capability in military equipment development. Today, as conflicts continue to demand precision and reliability from military forces, Chen's tiny baffle stands as proof that sometimes the most profound changes come in the smallest packages, transforming not just weapons, but the very nature of precision warfare itself.